All right, 610, number 6. Sir lost a lot on his drawbridge. The hardest part about this problem for me is just the stupid first part where you have to do some geometry or some trigonometry, right? So basic setup, drawbridge, length L, little l, which is given and different for everyone. Some constants are that the rope is attached 5 meters from the hinge, so that's the same for everyone. And our hero here is 1 meter from the end. So regardless of what the length of the drawbridge is, those are all consistent. And the rope is attached 12 meters from the hinge above it. So you can't really do anything with your forces or your torques until you figure out beta. You got to figure out the angle the string is making with the drawbridge, and the prompt already tells you that you can't assume it's 90 even though their diagram looks like it is. So we got to figure out beta. We can't figure out beta without knowing the length of the rope itself because of the fixed 5 and 12 distances from the hinge. Depending on what your L and your beta should be the same for everyone, and then this dude's just further out based on total L, little l. So just doing a little figuring there, we got to use the law of cosines to get big L, the length of the rope. I ended up getting 11.32. Problem also says don't round in your intermediate steps or your old answers. So keep all your numbers in your calculator for the whole process. So you use law of cosines to get L. And then you can use the law of sines to get beta. So you can get beta, which is the angle the string makes relative to the drawbridge. I got about 85.44 degrees. Once you got beta, then you can start breaking up your forces to figure out your torques. Okay, so that's the next step is we got to figure out the tension in the string using our torques. So the hinge point is also all obviously going to be the pivot point here. So all our forces then are at angles, and I guess that makes this one a little more tricky than some of the other static equilibrium problems, is everything's at an angle. So we got M1G, so M1 just being the mass of the bridge acting at the center. So we got that, and then we got our hero acting 1 meter from the end, M2G, and I'm going to break those into components perpendicular to the bridge. So boom, boom, you can see that there. Very similar to how you would find, the forces on a ramp. And then we got our tension acting at beta relative to the bridge, and we want to break that into perpendicular and parallel components as well, so we can sum up our torques, right? So we got beta now, and we got our 20 degrees that's making. So then our torques are M1G cosine 20, you finding this component here, right? This is our 20 degrees, times L over 2, because it's the center of mass acting half of the given length of the bridge. I'm going to call that the positive direction, that the falling bridge is the positive direction for rotation. And then our hero near the end of the bridge, he's acting 1 meter from the end. So we got his weight force, but only the perpendicular component. So again, cosine 20. And then he's acting 20 from the end point. Sorry, 1 meter from the end point. So you got your L minus 1 to figure out where that's acting. And then I ran out of room. So those are both positive torques causing the bridge to want to rotate or fall downwards. But the string and the tension is what's holding it up. So then I got a new line here. So plus, plus, minus then the tension sine beta times 5. And that is then the torque that's holding everything up. The two weight forces are trying to make it rotate down. Tension's rotating up. And so we got a negative torque from there. Set those guys equal to 0, and you can get your tension quite easily once you've got all your angles set. Okay, hopefully that makes sense. So then you have your tension, and then once you have your tension, you can go into finding your hinge forces. Now, the way the prompt asks us, it asks for the hinge force components, horizontal and vertical, which means we don't need to break the weight forces up, but we got to break that tension into an X and Y component. So we got to use beta again, but slightly differently, because now we want horizontal and vertical relative to, like normal horizontal and vertical, not perpendicular relative to the ramp. So summing up our forces in the X direction, we got our hinge force to the right. We know the hinge force is going to act to the right because there's only one other horizontal force, and it's acting to the left. Knowing those got to add up to 0, horizontal hinge force has to be to the right. You can also think about it, right, as like the tension is bringing it into the wall. If you look at the quick demo I did on static equilibrium, I had my setup on the wall, very similar to this. And that's actually, the tension's actually pulling the whole drawbridge into the hinge, right, pulling to the left. The hinge responds by pushing right, and then those balance out, add up to 0. Then the tricky bit here, right, is we can't use beta. We got to use beta minus 20 degrees because we actually need horizontal and vertical components there. So not using beta, but beta minus 20. Then summing up the forces in the y, we've got only 2 vertical forces. We've got the tension in the y here, right? It's holding the bridge up, if you will. So tension sine beta minus 20 for that up component. The hinge is also holding it up. You can just put them in as positives and then let the math tell you the direction of the hinge force. I like to just do it conceptually if you can. In my mind, if this hinge force isn't there, then this bridge is going to want to just fall down. The string's going to pull it up and it's going to rotate downwards, so then the hinge is holding it upwards, if that makes sense. I do a mental trick, kind of like what I do with friction. I try to picture what would the hinge do, what would the bridge do if the hinge wasn't there, and then I make the hinge forces oppose that motion and hold it in place. So vertical component from the string, vertical component upward from the hinge, and then 2 weight forces, also already vertical, so no trig to do there, just M1G minus M2G. Those are our 2 downs. A little bit of algebra, the 2 down weight forces, then minus the amount that the string is pulling up is then how much the hinge force has left to pull up. All right, that's your drawbridge problem. Number 6, where everything is static. And number 7, we're going to cut that string and we get a whole new problem to do. So see that in the lineup.